Now, what if I don't want to do simulations? And personally, this is my favorite chapter of all of statistics. Probability is probably the most challenging, most difficult chapter, but it's also the most fun. You're going to really enjoy working through the laws and rules of probability. We'll spend more time on simulation in our classes. What is probability? We define that as the outcome of a chance process. It's any number between 0 or 1, any percent between 0 and 100%. Well, we have to start talking about the language of probability. We need to know how we define certain ideas so that we can easily talk about the formulas and look at how probability works. Okay, so the first definition we're going to look at is a probability model. It's the description of the chance process that consists of two parts to a probability model. Okay. We need a list of all possible outcomes and the probability of each outcome. So, for example, flipping a coin, what are my outcomes? Heads, tails. Okay. What is the probability of each one of these outcomes? Oh, 1/2, 1/2. So, outcomes and the probability of those outcomes. This constitutes a probability model, the list of all possible outcomes and the probability that goes along with each of those outcomes. The list of all possible outcomes is called the sample space. So when they ask you the sample space, you would have to list out everything that could possibly happen. So if you think about the sophomores, juniors, and seniors that we tried to simulate previously, the sample space would be sophomores, juniors, and seniors, the list of all possible outcomes, and then the probability that corresponds to each of those outcomes. So very important. Sample space is usually written like this, with these big funny looking parentheses. So the sample space of rolling a die would look like this. 1, 2, 3, 4, 5, 6, even though I didn't quite get my whole 4 in there. All right. The sample space of flipping a coin, heads and tails. The sample space of choosing a student for my AP class would be sophomore, junior, senior. So the sample space is just a list of all possible outcomes. If I want to turn that sample space into a probability model, then I would have to assign the probabilities to each one. Like this was 3%, and this was 76%, and this was 21%, or whatever those numbers were. This was 1/6, 1/6, 1/6, 1/6. By adding these probabilities, I've turned these sample spaces into probability models. An event is any collection of outcomes from the sample space. So let me clear this off here. For example, an event could be the probability that I roll an even number on the die. That's an event. The probability I roll a 2. That's an event. The probability I pick a junior, that would be an event. The probability that I flip heads, that can be an event. So an event is just whatever it is that we're trying to find the answer for. Okay? If each event is equally likely, such as flipping a coin, rolling a die, then probability is quite simple. Our book here, for some reason, has messed up, and we'll see a lot of stuff that looks weird. Let's just cross that out. What is the formula for probability in general? What is the probability I flip heads? Well, it's on the coin, how many heads are there? 1. How many possible outcomes are there? 2. So the number of outcomes in the event divided by the total number of outcomes in the sample space. So let's look at this one where I want to know, rolling a die, what's the probability of getting an even number? Well, if I look at the formula here for probability, the number of outcomes in the event A. Well, on a die, how many outcomes are even? Oh, the 2, 4, 6. So there's 3. On a die, how many Total number of outcomes are there? 6. Oh, so the probability I roll an even number on a die is 3 out of 6, or 1/2, or 0.5, or 50%. I know these are simple examples, but just trying to show you why and how this formula here works. Okay. So we are going to talk about events A and B throughout this when we're looking at our formulas. Okay? It's just event A could be whatever it is that the question that we're trying to answer. Now you notice up here on the top, it's the complement. It's not, hey, you got nice shoes, I like your hair. The complement of an event means everything that's not that event. So the complement of flipping a head would be flipping a tail. The complement of rolling a number 3 on the die would be 1, 2, 4, 5, 6. Everything that's not that value. So the complement is written with a little, it looks like to the power of C. This is the complement of A. It means everything except A. Okay. It's the probability that A does not occur. So for example, what is the probability of the complement of a 3? That means I roll any number except a 3. So that's 1 minus the probability of rolling a 3. So this would be 5/6. Very important that we understand the language of probability. The little power of C at the top doesn't mean A to the Cth power. It means the complement of A, everything except A. Okay. Now we're going to talk about mutually exclusive events. Mutually exclusive means that the two events have no outcomes in common. They can never occur at the same time. Okay. Or another way to think about it is that the probability of the two events A and B happening is 0. And we'll talk about that more in a little while. Mutually exclusive events would be flipping a heads and a tails. You can't. It's impossible. You can't be both a heads and a tail at the same time. They can't occur together. What's the probability I randomly select a student in my class? One student and they are both a male and a female. It can't happen. So mutually exclusive means the two events can never occur together. If two events are mutually exclusive, then we simply add their probabilities together. For example, mutually exclusive events. What's the probability that I flip heads or tails? Well, since those are mutually exclusive, I take the probability of flipping heads is 1/2 plus the probability of flipping tails is 1/2. So that answer is 1. Very important for us, these words in probability. We're going to come across these words all the time. Not, that means complement. We're going to see this word or. Or is the union of two events. Or we'll use the symbol U. When we see or, we're going to think we need to add something. Or tells us add. Okay. We're going to see this word a lot in probability, and. And means the intersection of two events, which is an upside down looking U. And when we see and, we're going to think, oh, okay, I need to do some sort of multiply. And it's going to be different depending on the circumstances. Okay. So what are the basic probability rules? Every probability has to be a number between 0 and 1. If I add up all possible outcomes or the sample space, it has to have a sum of 1. It has to add up to 1. The equally likely outcomes, like flipping a coin, rolling a die, those kind of things, we know how to find the probability. The number of favorable outcomes over the total number of outcomes. This formula right here. The complement rule. The probability of not A is the same as 1 minus the probability of A, like the example that we just looked at. And then the last thing that we've looked at so far is mutually exclusive. If two events are mutually exclusive, meaning they cannot occur at the same time, then the probability of A or B is just A plus B. All right, let's get a little more in depth with the probability rules. The general probability rule says if A and B are any two events resulting from some chance process, the general addition rule, the rule that works always, no matter what, guaranteed every time, is this rule that we see right here. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This rule works whether the two events are mutually exclusive or not, because if you recall, if the two events are mutually exclusive, then the probability of A and B equals 0. So this chunk here would just go away if the two events are mutually exclusive. Okay? So this general rules and probability mean they work all the time. So for example, what is the probability that I am a male or a female? Well, the probability that I am a male is 90 over 178. Plus the probability that I'm female is 88 over 178. The probability that I am a male and I am a female is 0 over 178. So the probability of being male or female is 178 over 178, which is equal to 1. Well, we know that. Every individual in this example is either a male or a female. Now, we're looking at, is there a relationship between gender and pierced ears? That's what this two-way table is telling us again. We're going to look at this two-way table over and over again, the same set of data. Okay, let's look. Do you think that being a male and having your ears pierced are mutually exclusive? If they are mutually exclusive, that means you cannot be a male and have your ear pierced at the same time. Well, we know that those two events are not mutually exclusive. It's possible to be a male and have an earring. Okay, so let's look at that. I want to know the probability of being male or having my ear pierced. So if we look at the formula above, that's the probability of being male plus the probability of having my ear pierced minus the probability of being male and having my ear pierced. So we can see here the probability of being male is 90 over 178. The probability I have my ear pierced is 103 over 178. If I add those two together, I get 193 over 178. Well, that breaks the first rule probability that every single answer has to be a number between 0 and 1. So I know that can't be the answer. I can't have a probability of 193 over 178 because that number would be 1.2 something. Doesn't make sense. These events are not mutually exclusive. Okay, they are not mutually exclusive because you can be a male and have your ear pierced at the same time. So when I did this, I took 90 over 178, 90 over 178, plus 103 over 178. Well, where did I get this 90 from? This 90 came from the males, the 19 and the 71. Where did I get this 103 from? The 103 came from the 19 males plus the 84 males who had their ears pierced. So this number that we came up with here of 193 over 178 came from the green and the red rectangles here. But what happened? Why is this wrong? Because when we looked at males, we counted the 19 and the 71. When we looked at ear pierced, we counted the 19 and the 84. Wait a minute, we counted these same 19 individuals twice. That's why the rule for the general addition rule says we must subtract the and. Why are we subtracting the and? Because we added it twice. So I'm going to take it away once. So 193 minus 19 is 174. So the probability that I am a male or I have my ear pierced is 174 out of 178. Okay? This is how the general addition rule is applied. I really like using this two-way table because you can see why we have to subtract the and, because this 19 right here was used twice. It was used in the males and the ear piercing. We can't count those same 19 boys both times, in the males and in the ear pierce. All right, let's eat, man.